All right. So today we're gonna cover probably the other main topics in linear algebra. Okay. So we have already looked at spans. Okay. Span and linear combination. Okay. We looked at that many times. Okay. And today we're gonna look at the other somewhat opposite concepts called linear independence. Okay, and these two concepts are roughly complementary, but and it should give you the whole picture of linear algebra. Okay, but before we're gonna do that, we talked about vector space first. Okay. Vector space. So what exactly is the vector space? Intuitively, vector space is a set of vectors that satisfy some closure properties. So basically, it's a set of vectors, okay, such that when you do something with it, the results remain within the set. Okay, so that's roughly. We will see the definition soon. Okay, so we will start with vector space, and then we give you a review on span, linear combination, and then we talked about linear independence. Okay. Okay, so let's have a quick review. So if you have vectors m1, u1, u2 up to um, and if you combine them by scale sum of the vectors and then you add them up, you get a linear combination. Okay. If you have a set of vectors and then you take all the possible linear combinations of them, we get a set of vectors that we call a span. So a span is the set of all possible linear combination of a set that you have. Okay. All right. So you should take the exercise sheet at the back of the room. Okay. So let's try the first exercise. So you given so you have three types of energy drink. Let's call it V, C, and W. Okay, V, C, and W. And we represent each of the healthy drink by the amount of nutrition that it has. We represent it as four vectors, a vector with four numbers. Okay, so the first number might represent the amount of I don't know, vitamin C. This is like sugar. This is the third one is what are the ingredients inside a healthy drink? Vitamin B, and the last one is like salt. Okay, you get some salt. I don't know. Okay, so if you take 100 milliliter of V, you get 100 grams or milligram of vitamin C and 50 something of sugar, stuff like that. So for each of the drink, you have three types of drinks, and for each of the drink you have these are the information that you have. Okay, so we describe this as a vectors. So we have three vectors for three types of drinks. Okay, and if I combine this drink, if I mix the drink like this, so I take 30 milliliter of V and 200 milliliter of C and 10 milliliter of W, what are the nutrition in the mixed drink? Okay, so you have a drink and you mix them up, and some of this like has like partly V and C and W. So what are the nutrition of this mixed drink? Can you represent it as a vectors? Can you write it down using vector V, C, and W? Okay, do that in the first exercise. So let me do that for the first for the 50 milliliter of V. So 50 milliliter of V, how much do you get for each of the nutritions? So you basically, this is for 100, right? So you get 0.5 times 100, right? And then you're gonna have the other three, and then you combine and you get the final thing here. Because this is for so you think of this as a, this is solution V, this is C, and this is W, right? And this is like 100 milliliters, and you take like half of that, right? So you're gonna get this, right? And then you take 200 milliliters of this, so you're gonna have 2C, right? Like that, right? So you're gonna have, you add 2 times 0, 0, okay? Each of these numbers, again, each of these numbers is a representation of the nutrition inside one bottle. So let's make it a bottle. One bottle of each drink. Okay. So we have four numbers. These 4 numbers might be anything, right? But for example, you can think of the first number as the amount of vitamin C that you get in milligrams in this drink, and the second one is the amount of vitamin A. I don't know, A, B, C, D, E, whatever. Okay. So if you take half of the half of the bottle, you will get 0.5 times these vectors. If you have 2 bottles, you have that. And finally, if you take 10 millimeters, so you get 0.1 times, okay? And what do you get as a final product? So what's the top number? What's this? Okay, so you can combine them, right? So each vector, you scale it, right? So this is like scaling vectors, right? Okay, then you combine it and you get this one, this final, the nutrition of the combined drink. Okay. Again, what is this vectors? What is this vector? This vector is a linear combination of vectors C, V, C, and W. Okay? It's a linear combination. Okay? You take vectors, you take a set of vectors and you scale it and then you combine it and you get these vectors. Okay? So do the final calculations. คำนวณให้เสร็จเลยครับหาคำตอบมา Okay, and then the last question for question 1 is like the question asks you to rewrite this sum, okay, in terms of matrix multiplications. Okay, in terms of matrix multiplication. So basically, you're gonna have a matrix that look like this. Okay, and you want to find a vectors that find this. Okay, so that the result is exactly what we did. Okay, so let's finalize this. So this is like 0.5 times 100 plus 0.1 times. So this is 5. This is 55. Right? And this is like 25. This is 600 plus 5. And finally, this is like 1. Yeah, so this is the final vectors. So we know that in the end, our mixed drink has these amounts of for each ingredient, for each nutrition that we are concerned about. Okay. So now we can write this. We can write this term. You can write this term as the matrix multiplications. Okay, this is a review. Last time we talked about how are you gonna think about matrix multiplication, right? So we have a matrix that represents these three column vectors, and we like to find out the vectors to multiply with it so that we get exactly like this. Okay, so you need to figure out these three numbers that would give you this. Okay, can you rewrite that in like this? Okay, so let me give you the solution so that we don't spend too much time reviewing materials. Okay, so let me zoom down. Okay, so when we do matrix multiplication like this, okay, ถ้าตรงนี้ใครไม่รู้จะทำยังไงช่วยฟังนิดหนึ่งครับจะได้ไม่งงโอเค when we do matrix multiplications there are two ways to think about it okay the typical way is like we start with each row right on the left we focus on the rows and then these rows got multiplied with the whole vectors and we get this first guy okay but if you think about this for a minute if you look at the next row, so this next row is gonna be got multiplied with this vector as well, okay? But if you think about this, just think about the first guy here, okay? So let's call it alpha 1, okay? So which number would got multiplied with alpha 1? Okay. So the numbers that got multiplied with alpha 1 are those in the leftmost columns, like the first columns. Okay. And the results is like you multiply alpha 1 with 100 and you add to this number, right? And you multiply alpha 1 with 50 and you add to that number. And 0 and 0 with alpha 1. So basically alpha 1 will multiply these vectors. Similarly, when you think about, if I call this alpha 2 and alpha 3, so this alpha 2 okay, will multiply with these column vectors. And finally, alpha 3 multiply with that, okay? So since we know that these numbers, okay, these vector is the result from the addition of this, right? From this. So this vector is basically a linear combination of that three vectors, right? So you multiply the first vector with 0.5. So alpha 1 here is going to be 0.5 and this will be 2 and this will be 0.1. Okay, so basically you can express this linear combination as a matrix multiplication like this. You take the matrix, okay, and when you want to think about linear combination of columns, you multiply the matrix with column vectors that basically the first row will get multiplied with the first column, the second row here will multiply with the second column, and finally the last guy in the last row will multiply with the last column. Okay, so this is how you write it as a matrix multiplication. Okay, all right. So this is a quick review of what we did so far. Okay. Okay. We'll come back and work on the exercise later today, but right now you can just leave it there. Okay. ทำเสร็จแค่ไหนก็ไว้แค่นั้นนะครับไม่เป็นไรแล้วครับเราเรียนต่อเลยเดี๋ยวจะไม่ทันยังไม่ต้องส่งนะครับเดี๋ยวเรียนอีกที Okay. All right. Okay. Quick overview. Quick review. Okay. So we have two vectors here in this example. You have 1, 2 and 2, 5. So let's try to visualize it. Okay, let's try to visualize these two vectors. So let's take the first number to be the x-axis. So 1, 2 is basically this vector. So this is 1, 2. And 2, 3 2, 5. Maybe this 2, 5. Okay. Using our vector as a point, or sometimes it's easier to draw an arrow with it so that you focus on the direction. Okay. Slightly. Okay. They are not in parallel, but my drawing might be bad. But okay. All right. So these two vectors. Okay. What is the span of these two vectors? What is the definition of a span? A span is a set of all linear combinations, right? So if we just look at the span of 1, 2, what is the span of 1, 2? If you have one vectors, the linear combination of that one vectors can only be just that vector with the scale, right? You can just scale it, okay? So the span of 1, 2 is going to be a line like this. What is the span of 2, 5? Again, it's going to be another line. Are they in parallel? Do they point to the same direction? No. Okay. Now, when you think about the span of these two vectors, you ask, what are the possible linear combination of these two vectors? Is it possible to get to anywhere in the plane with these two vectors as the basic direction? Yes, right? If you want to go to this point, for example, you want to go to this point, you basically go on this direction and then you come back with that direction slightly and then you come back to this. Okay? You can see that by combining these two vectors appropriately, you can go anywhere on the plane, right? So the span of these two vectors is r squared. So r squared is the entire two-dimensional space. Okay. If you can reach any point using these two directions, it means every vectors in r squared is a linear combination of 1, 2, and 2, 5. So the span of 1, 2, and 2, 5 is r squared. Okay. Now, let's look at the three-dimensional case. Okay. We have this vector 1, 1, 0, 1, and 1, 1, 0, and 2, 3, 4. Okay. So what does the span look like? Okay. To think about this, first of all, let me try to recap this a little bit. So if you have two vectors and they are not in parallel, okay, they do not point to the same direction in two dimensions. The span will look like a plane, okay, because the first vector gives you a line, the other vectors can shift your line to wherever you like. Okay, one way to think about this is like this. So you have the first line. So if you add this, so this is a linear combination of the first vector, right? If you have a second vector which are not on this or in parallel, you can sort of like shift this line wherever you like, right? You can shift it to this point, on that point. So when you can shift it around, so you can cover the entire plane. Okay. So if you have two vectors that are not in parallel, you get the span of that two vectors will be a plane. Okay. Two-dimensional plane. Now, if we have let's look at the case in 3 dimensions. Let's look at that. Let's look at the case with two vectors first. Are these two vectors do they point to the same direction? No. Okay. So the span of these two vectors, what should it look like? Can you imagine that in your head? ข้างหลังครับฟังนิดนึง What does this span look like in class? Okay, so if you have two vectors, and they're not in parallel, the span of that you get is a plane. Okay, so if you have a three-dimensional space and you have like maybe that's another vector, the span will look like that. Okay. Okay. Like that. Okay. Now, if you add another vectors, if you have two vectors and you add another vector, in this case we add this vector, right? We add this vector. If the vector that we add is also in this plane, can you change the span? Can you make the span bigger? If you already have a span and you add another vectors, can that give you a different set of linear combinations? You won't, right? Because you cannot, that vector belongs to the plane, so it's already a linear combination of the first two vectors. Okay? So suppose, let's forget about this guy for a minute. So suppose I consider this span of this one and that one and the next one. Can you come up with a vector which is a linear combination of the first two? ยกตัวอย่างเวกเตอร์ที่เป็น linear combination ของสองอันแรกให้นิดนึงครับอะไรดีเอาง่ายๆ 2 1 1 so if I add these vectors will I change the span? No, because this guy is already in this plane, right? So by adding this up, you cannot get out this plane because the vector that you have is already on the plane. You can just shift the plane around. Okay? So adding a vector inside a span won't increase the span. Okay? Now think about 2, 3, 4. Is this vector belong to the span of this set? Is it belong to the span of this two? This question is like you ask, is it possible to write 2, 3, 4 as a linear combination of, can we write 2, 3, 4 as a linear combination of 1, 0, 1 and 1, 1, 0? Can you do that? Can we write this as a linear function of that? No. Why is that? Why can't you do that? One way to look at this is like, if you look at the last coordinate, right? Only the first vector has some component, non-zero component in the last coordinate. So if you want to get 4 here, you need 4 units of the first vectors, right? So you need 4 times 1, 0, 1 to ensure that you get 4 here, right? And also if you look at the second coordinate, which is 3 here, so to get 3 here you need 3 units of that. So right, so this is the vector that you get I think 7, 3, 4, right? So if you want to get 3 and 4 in the last coordinate, the first coordinate, the first value can only be 7 if you made it up from the first two vectors. Okay? So this is like the constraint that you have when you only have vectors, two vectors. So you know that 2, 3, 4. Okay, this vector is not in the span of the first two vectors. When you think about this, it's like you already have a plane, okay, and you have another vectors that, so this is a plane, and you have another vector that is pointing out of this plane, okay. By adding this to the set, we can ensure that we can shift the plane around, right? So right now we have a plane. If we can move the plane around, so we can go anywhere in the three-dimensional space, okay? So the span of these three vectors is R, R cube. Okay. All right. So linear algebra is nothing that difficult. Okay. But you need to be able to imagine stuff in your head. Okay. The first time you do it, it's not easy. But if you keep doing that, you get crazy. No, sorry. You might get crazy because like when you see your friend doing the cheerleader thing, you like, oh, that's another plane, or he moved the plane like that. You can do that. It's nice, but yeah, you can get mad. But try not to get mad. Okay. How about this? Is the span of this R cube? Okay, you can use the same reasoning, right? The first two vectors are not in parallel, right? But the third one belongs to the span of the first two. Is this belong to the span of 101 and 110? อยู่ไหมครับ อยู่ปะ Yes, because you can add two times this and 2 times that, and you get this one, right? So now in the case you know that, oh, this is not. The answer is no, because this is not equal to R cubed, because you only get a plane out of 2 vectors. Okay. All right. Okay. Let me talk really quickly about what's inside a vectors. We'll come back to that next on Thursday when we ask you to do some experiment on error correction code. Okay. And we will play some games. Okay. So previously, what's inside the vectors that we talked about are real numbers. Okay. You can also have complex numbers inside the vectors. Okay. But you can also have some other things. And what we've learned so far and what we will learn later on will pretty much work on the other types of numbers. Okay. What are these other types of numbers? So let me show you one thing. We'll come back to that on Thursday, okay? But let me give you some motivational example. Typically, what's inside the vectors in linear, in like machine learning, AI, are usually real numbers, okay? So we call this a vector over R. Over means like elements are in this guy in elements of the vectors are in R. Okay, so you can multiply with 0, 1. You multiply with 10 with 1.0. No, 0.1. Stuff like that. You can divide by 2. Okay, so because it's a real numbers, you can do stuff with real numbers, right? But it doesn't have to be in just real numbers. Okay, it can be some other form of numbers that support some of the operation like this. Okay, so these are the operations that we need so that we can use it as a vector. So basically, just the real numbers. You can have add, plus, and multiplications over these numbers. Real numbers is one example of this thing, but there's some other thing as well. So I'll come back to that on Thursday when we actually see some concrete example. So I'm gonna leave it here. Okay. So we look at this GF2. Okay, it's a big field. Okay. Okay. We will come back to this on Thursday. Okay, when we play some games. Okay. Okay, I'll go over it really fast. All right. Okay, so now we recently we talked about spans. Okay, what does a span look like? So a span of one vector, a single vector is a line, right? If you have a span of 2 non-parallel vectors, you get a plane. Okay, if you have 3 of that, if they're non-parallel, you probably get the whole space. But you can have, if you think about higher dimensional space, it might look somewhat like a plane, but we call it a hyperplane. Okay, so when you take a span of vectors, you get what we call a plane or a hyperplane. Another way to get this kind of thing, okay, you think about what we talked so far. In 2 dimensions, okay, if you take these vectors and you take a span, you get this line, right? But you can also express this line as an equation. Okay, you can express this line as an equation. So the equation might look like x minus y equals 0. Then you get this line. Okay, so there are 2 ways to express this set. Okay, when you look at the line, it's not just a line; it's a set of points. Okay, there are 2 ways to express this set. One is as a span, another as the solution of linear equation. Okay, in 3-dimensional space as well. Okay, when you have 2 vectors, you can think of them as a span. You can take a span of these 2 vectors, you get a plane, right? But when you take one linear equation, the set of all solution of that linear equations also look like a plane as well. Okay, but that kind of linear equation has to be has to go through 0. Okay, so there are 2 geometric objects, 2 types of geometric. There are geometric objects that can be expressed in 2 ways. One as a span of vectors, another as solution of a set of linear equations. Okay, but these are linear equations where the right hand side coefficient or constant are all 0. We refer to them as homogeneous linear equation. We'll come back to that soon. Okay, but this set, okay, this set has a nice properties. Although it can be expressed in 2 ways, they are the same thing. Okay. Okay, they are the same thing. So we will define what we would call a vector space. Okay, so this object we refer to as vector space. Okay, but what are the common properties of these objects? Okay, first of all, they pass through the origins, so they contain 0. And if vector is in the object, you scale that vectors, you also belong to that object. And finally, if you have 2 vectors in that object, you add them up, it also belongs to that object. Okay, so if we have an object like this, okay, we will refer to it as a vector space. Okay, so we define a vector space to be a set of vectors over some field. So you can, when you see F, you think of this as R, but it doesn't have to be real numbers. Okay, it can be something else that we'll see on Thursday. But you think, for now, you think of it as R. Okay, so we say a set of vectors is a vector space if and only if. Okay, first of all, it should contain 0. Okay, a set of vectors that contain 0, and if you take any vector inside it and you scale it, it remains inside the set. Okay, so mathematically we say that this set is closed under scaling. When we say it's closed under some operation, it's like we take a vector from that set, we perform some operations, the resulting vectors also remain in the set. Okay. For u inside V, if you multiply u with some scaling factors, result is still in V. Okay. And finally, if you take 2 vectors inside V and you add them up, and it's also inside V. Okay. So if you have a set of vectors like this, okay, that satisfy these 3 constraints, we refer to that set as a vector space. Okay. why do we need to talk about vector space? It's basically we can manipulate vectors, but sometimes we would like to see the set of all possible vectors that we can generate, or sometimes we would like to think about, okay, what are the possible inputs that we have, okay? Those are the set of inputs, right? So we need to have some way to talk about all of them. So that's what we call vector space, okay? Okay, so I'm gonna go over this really quickly, okay? So if you have a set of vectors, the span of the vector is a vector space. Okay, so if you take vector, you have vectors and you take the span of them, you get a vector space. Okay, why is that? So why is the span of a set of vectors is vector space? So basically, to show that, you need to go back to the definition of vector space. Okay, and you need to check all the three property if these three property holds. Okay, so you need to check if you want to show that the span of this is a vector space. Okay, so you need to check, first of all, you need to check if 0 will belong to this set. Let's call it set A. Then you need to check the second property such that that is like for all vector u inside A, for all alpha, alpha u belong to A or not, right? Need to check this. We need to check this, and finally we need to check V3. We need to check that if we take any vector u and v from A, u and v it still belong to A or not? Belong to A. So this is like, you recall this? อันนี้อะไรครับครับจากอาจารย์ธนะ Okay, you should remember อาจารย์ธนะ Okay, อาจารย์ธนะ who has earphone on all the time. Okay. When you see this, you think about okay. So I need to cut this out from my video. I probably won't. Chantana won't watch the video anyway, so nobody sees it. Okay, don't tell him. Okay, so we need to check these three properties. So let's do that really quickly. Okay. So V1. Okay. So a zero vector belong to the span because 0 belong to the span because 0 is a linear combination of this, right? Because 0 equals 0 times u1 plus 0 times u2 plus and so on plus 0 times um. Okay, so the first property holds. If you take another vectors, like let v belong to span of u1 to um, we want to show that alpha v is also belong to the span, right? How can we do that? So since we belong to the span, so what does this mean? What does v belong to the span means? It means that v is a linear combination of u1 to um, right? The fact that v is a linear combination of u1 to um, what does it mean? So it's a linear combination, so we know that there exists. So this is a Chantana again. Some constant alpha 1, alpha 2, up to alpha m, such that alpha 1, u1 plus alpha 2, u2, and so on, alpha m, um equals v, right? Okay. Now, if we consider alpha v, okay, so alpha v is going to be, oh, okay, I just use the same symbol. So consider some beta v, okay, some scaling of v. So beta v is going to be beta alpha 1 u1 plus beta alpha 2 u2 and so on up to beta alpha m um, right? And this is also a linear combination of u1 to um, right? Because you have some numbers, you scale u1 by something, u2 by something, you add them up. So this beta v is also a linear combination of vector u1 and to um, right? So this implies that beta v is also in the span. Okay, so this second property has been checked. So you can also check v3. Okay, so you take two vectors and then you add them up, and then it belongs to the same. It will also belong to the span. So you can do that. That's pretty straightforward. So I'm gonna skip it. So you can also check v3 as well. Okay, so this set is a vector space. Okay. Now the other thing that is also a vector space is a set of homogeneous. Is a set of solutions of the homogeneous linear equations. Okay, but before we can prove that as well. Okay, we can prove that as well. But before we do that, let me again show you geometrically what this look like. Okay, เดี๋ยวไปดูรูปกันนิดนึงก่อนครับจะได้ทบทวนด้วยนะครับ Okay, so this is three-dimensional space. So let me show you let me show you one equation. So x plus y plus 2z equals 0. Okay, so this is the first equations, and it looks like a plane. So let me move it. It's a plane, right? Okay, can you see that it's a plane? Okay, so since it's a plane, if you take one vector inside it and you scale it, it will also belong to a plane. Okay, and also because the constant here on the right side is 0, this one is 0. So if you set x to be 0, y to be 0, and z to be 0, it belongs to this set. It's a solution of this equation. Okay, so 0 belongs to this plane, and if you have one vector inside it, you scale it, also belong to the plane. And also if you take two vectors and you add them up, it also belongs to the plane. Okay, so this plane is basically a vector space. Okay, now you can get a vector space not just one equation. If you have another equation, if I add another equation, okay, if I add another equation, this equation alone has a set of solution to it. Okay, that looks like this. This plane. Okay, now we have two planes. Okay, so the three axis is basically the xyz axis. So you can sort of like turn it around. Okay, so that you can sort of like view these two planes. Okay, the green plane. So I have two equations here. Okay, so if I just hide so the first equation, x plus y plus 2z equals 0. Okay, the solution, the set of all solution of these equations are the set of points that satisfy these equations is shown as this green plane. Okay, so why does it look like a plane? Because this is an equation, right? This equation has three variables. When you have three variables, it's like you cannot satisfy this equation by setting all. You can just say, you cannot say like, I want x to be 10, I want y to be 7, I want z to be 25, and get this equation satisfied. Okay? You cannot freely set three variables at the same time to get so that this equation remains satisfied. But you can basically set two. When you have three variables, if you set two variables, the third variable can be computed from the first two. Right? So if you set x and y, you can solve for z. Okay? So for every, okay, so here you have x and y. Where is x and y? You have this x and y, right? For any possible value of x and y, you have another value of z. Okay? So if you plot everything based on x and y, you can see like you have some value of z. So it looks like a plane. The reason for that is that if you change x a little bit, okay, if you have a point on this, if you have solution, if you change x a little bit, okay, you need to change z a little bit as well, right? But the amount of change in value of z is going to be half as much. If you increase x by 1 unit, you have to decrease z by half a unit, right? Because x has a coefficient of 1 and z has a coefficient of 2, right? So if you have a point satisfying these equations, so let me write it down here. So you have this point satisfying x plus y plus 2z equals 0. And if you change the x-axis a little bit, okay, so this decreased by 1 unit, you need to increase the value of z, right, to compensate the change in x. But you only need to increase the value of z by half a unit, okay? So if you fix y, x and z, the relationship between x and z is linear. So if you change x by a lot, you need to change z by a lot as well. If you change x by a little, you need to change z by a little as well. And it's proportional, right? So for any unit of change in x, you need to change half of that for z, okay? So the relationship is linear, so you get a line, okay? Okay, so for each value of, you start with 0, right? You keep increasing the value of x, you need to decrease the value of z, okay? So you get a line. If you move on the y-axis, same thing happens. So the set of solutions that you have will look like a plane because everything is like a straight line. Okay? So this green plane is the set of the solution of the first equation. This purple plane is the set of solution of the second equation. Okay. What is the set of solution of this system? Okay. When I talk about the solution of this system, I want a set of points that belong to both, that are solutions to both equations. So the points satisfy both equations. What are they? What are this set? What is this set? Can you see it? So you take the section between these two planes and you get this line. Okay? Okay. So this is the set of all solutions of this system. Okay? When you talk about a system of linear equations, you want a point that satisfies all equations. Okay? So it's the intersection of each of the set. Okay, so you get a line like that. All right. So if you don't just have one equations, if you have in this case m equations, no m, how many equations? M equations. Okay, the first equation, second equation, up to m equations with n variables. Okay, if you take the set of all solution for this system, okay, in this system we have m equations. Okay, they also form a span. They also form the vector space. Okay. The reason for that is that if you put 0 to all the variables, this set of equation is satisfied. So property V1 is true. Now, if you have two equations, so to prove this, maybe I need another notation. So this equation, this way of writing equation is kind of like very cumbersome. So let me give you another definition. A dot product. We learned about dot product previously, right? So if you have two vectors, a dot product is like you multiply each of the corresponding vector elements and you add them up. Okay. So with this, so if you use dot product, okay, the first equation can be rewritten like this. So you set vector x to be vector x1, x2 up to xn, and vector a1. Let me mark the dash on the top of the variable to say it's a vectors. So let a1 be a11, a12, a13, and so on to a1n. Okay. So this equation can be rewritten as a1 dot x1 equals 0 dot x. Sorry. So if you have, you can rewrite all this like this, and you get this set. Okay. The set of all this set belongs to R to the n because you have n variables, and it satisfies this the first equation, second equation, up to the m equations. Okay, so this set of all possible solution of this m equations. This is also a vector space. Okay, to see that you can see that if I put x to be 0, all the equation is true. Okay. Now to check if it's a vector space, I also need to check if I can scale a vector and still it belong to the set or not. And also if I take two vectors and add them up, do they still belong to the set or not, right? So I can do that pretty easily by looking at if I have x as a solution, if I have x belong to the set S like this, alpha x also belong to this because I can check if alpha x times a1 equals 0 or not, right? So, but it's a dot product, so I can switch order. So it's a1 dot x, okay? But I know that this is 0, so 0 times alpha, and it's alpha. So property V1 holds. Property V2 also holds because if I have x and y belong to this set, I can add them up, okay, and multiply to a1, right? So this is a1 x plus a1y. But I know that x is a solutions and y also a solution. So they are equal 0 plus 0, so it's 0. So if I have solutions to this set of linear equations, I can scale it, and the result belong to is also a solution. I can take two solutions and add them up. The result is also a solution. So the set of all possible solutions is a vector space. Okay. So two things. So let me conclude really quickly. Okay. a vector space is a set of vectors, okay, that has these properties. The first is like 0 is belong to the set, and then it's closed under scaling. If you have any vector inside the set, you scale it, it's still a vector in the set. And also, if you take two vectors in the set, you add them up, it belongs to the set as well. If you have these three properties, we call that set a vector space. Okay. Currently, there are two types of things that we know that they are vector space. One is a span. You take a set of vectors and take the span of it, it's a vector space. The other set is like, if you have a set of linear equations that are homogeneous. Homogeneous linear equations are those with the right-hand constant 0, okay? If you have this, we call them as homogeneous linear equations. Okay, a solution to this set of homogeneous linear equation is also a vector space. Okay, two things. Okay. All right. These two concepts will come back. Okay. Right now it's very theoretical, but you see it come back really soon. Okay.